All right, so today we're going to finish up Unit 1 for our Algebra 2 here. Okay, so we're going to cover lessons 1.7, 1.8, 1.9, and then 1.10 will be for you to look over for homework. That's the wrap-up section, okay? If I can gloss over this quickly. All right, lesson 1.7 has one quiz. There's two quizzes in 1.8 that you have to take, and then there's this extra credit journal, all right? In 1.9, there is a quiz that is mandatory. And then in 1.10, if you'd like to do the review, that is also optional, okay? So all of that, okay? And then you're only required to take this CST, all right? Not the TST. I'm pretty sure I unlocked all of your CSTs. As long as you started the course, that should be unlocked for you. But if for whatever reason yours is not unlocked or you're having issues taking that test, please reach out to me and let me know as soon as possible so I can get that fixed for you. All right, looking here at lesson 1.7. So we've been dealing a lot with these rational functions. Okay, we've been dealing a lot with rational functions. So now we're going to deal with how do we actually solve them and what does that look like. So looking at our rational functions, again, to remind ourselves, it has this form a over b, where a and b are both polynomials. All right, a rational function is a function whose equation contains a rational expression, and I hate that definition. It uses the word in the definition. All right, but again, it could be a monomial, a binomial, a trinomial, any of those things, right? But it has to be a rational expression in order to be a rational function. Okay, so if we look back here at our painting problem, right, it was that inverse variation. Okay, so it was that inverse variation. It was also a rational function. All right, so if we look at that width, it was the width equals 100 divided by, sorry, our height equals 100 divided by our width, right, in order to cover the paint. And we talked a lot about that yesterday. But what we can do is we can take this equation that we have and we can turn it into a function. All right, so what we do is we change one of our terms here, so we have width, and we can change our width term here, and we can change that into a variable w, and what we can then do is make height a function of w, right, a function of width, because that's what it is, basically. It's what it's saying is it's determined, or the value for height is determined based on whatever value you put in for width. That's what it means. So we can rewrite our expression as HW equals 100 divided by W, right? So our function of height, or height as a function of width, is equal to 100 divided by width, is what that's saying there. Okay? So again, just to remind ourselves here of what this looked like. Okay, so if I drag this along, okay, I can see it has that inverse relationship, whereas one goes up, one goes down, and they go by up or down by the same factor here. All right, and if we're looking at domain, right, those are the x values that we can put in, right, or our width values. So what we can see here is that we can get really, really far out, and looks like we can get really, really close. But if we think about it, we can't actually ever have a width of 0, because if we have a width of 0, we're covering no area, right? So we can have anything as long as it is greater than 0, right? It has to be greater than 0. So again, our domain of h of w is greater than 0, right? It doesn't include it. It has to be greater than. All right, it has to be greater than. And as I get really small or really large, I still have to have 100 as my area that I'm covering. All right, when I look at my range here, those are my y values or my output values. So you can see here that as x gets really, really small, it looks like my y just gets infinitely larger, right? But as I keep going with my width larger and larger and larger, okay, eventually I'm going to get really, really close to 0. But again, the same problem. I can't ever have 0, because if I have 0, then I don't fulfill my 100 constant value that I need for my area. Okay, so my range here is going to be greater than 0. So you could write this as y is greater than 0, h of w is greater than 0, height is greater than 0, right? Whatever. But my output values have to be greater than 0. And you can notice here that both for my range and domain, neither of those values are negative. All right, neither of those values are negative. Right? And if we're thinking back to our original problem, it kind of makes sense. I can't negative cover a wall, right? With paint, I can't negatively cover a wall. That would be removing paint, and that's not what we're trying to do here. We're trying to cover the wall with paint, and we only have enough to cover 100 square feet. Okay, so those things we kept saying, it approaches, it gets really, really close to, but it's not touching. Okay, so those are what we can call asymptotes. All right, asymptotes. And what this means is it's a line where the function gets close to touching that line, but it never crosses, or it never touches. Sorry, it never touches. It's really, really close, but it never touches. All right, and we can have a horizontal asymptote and a vertical asymptote. So again, our horizontal would be like a horizontal line. So the line of W equals whatever. So right now, our asymptote that's horizontal, that point that it's approaching but not going to touch, is going to be x equals 0. Right, that makes our horizontal asymptote. Similarly, we can have a vertical asymptote. Right, we can have a vertical asymptote, and that's a vertical line where it never touches. So for example here, our vertical line would be at x equals 0. We can get really, really close to 0, but we're never going to touch it. Same thing, we can get really, really close to y equals 0, but we're never going to touch it. So those are our two asymptotes. Right? We're going to work a lot more with that later on here, but good introduction. Okay, so then if we go back to our lever problem here, okay, if the input is the distance between the lever's fulcrum and the right-hand pan, we can use the variable d for distance. All right, and what we're saying for our output is the mass needed to balance the lever. All right, so we're saying this function we're going to call as m of d, right? The mass needed to balance based on our distance. Okay, and what we can do is we can play around with changing the distance on this guy here. And obviously if I'm at 115 and 115, okay, I need an equal amount of weight. If I move this farther out to 150, now this is actually too heavy. So I can get rid of this. Oh. And let's say maybe add 400 and see what happens. Oh, 400's too much, right? Getting closer. Okay, so I didn't need quite even 400, right? So I think I have 360. All right, so as I moved my distance further out, I needed less weight. Okay, but now if I move really close, so let's say 50, I have 50. 500 is not enough weight. 1,000's still not even enough weight. It's getting closer. Too much. Right, and play around with it. But basically what you're going to find out is there's an inverse relationship between how much weight I need and the distance between the fulcrum. Okay, so there's an inverse relationship between them. The closer I get, the more weight I need. The farther I go, the less weight I need, right? So that's an inverse relationship. All right. So if we were to pick those specific points, 50, 75, 100, 150, again, we could look at how much weight we need for different points. So if I'm looking at, again, my 900, I would need less weight out here. I would need less weight out here. Oh, that's still too much. And again, you can play with this on your own here if you have that capability. All right, but so it's somewhere between those two, right? It's somewhere between having that 10 and not having that 10. But you're going to notice here that if we collect data points, again, like I said, we need more weight when we're farther away, and we need less weight when we're farther away, and we need more weight when we're close up, right? We need more weight when we're close up. Still, again, you guys get the point here. All right, so there's an inverse relationship that we could take some time and find the data, but luckily Apex already found that data for us. So if we were to plot those points, right, it would look something like this. And you can kind of see it's having this inverse curved relationship here. All right, and what we can notice here is that when we doubled our input, right, so we went from 50 to 100, our output was halved. We went from 2,000 to 1,000. Or when we went from 75 to 150, that's double. We had to halve our output. Okay? Or again, from 50 to 150, we multiplied by 3 to get from 50 to 150. We had to divide 1,000 by 3 in order to get our output. Okay? So what this is showing is that we have an inversely proportional relationship. Right? We have an inversely proportional relationship. So again, if I double my weight, I'm going to have my distance, or vice versa. Right? It's got a relationship where whatever I do to the input, it has an equal magnitude, just the opposite sign, right? So again, double, divide by 2. Multiply by 3, I'm going to have to divide by 3. All of that stuff. Okay? So knowing this type of inverse variation, it can be really, really helpful. Okay, now what we can do here is we can look at different points along the line, right? And we can see here, if we can drag and we can look at different combinations to predict how much mass we might need, right? So using this relationship, okay, using this, if we were able to find a graph, we could say, okay, if I only want to be 58 distance apart, how much weight am I going to need? Or if I only have 500 pounds in order to balance this, right, I'm going to have to be at least 200 away, right? You can use this relationship here to figure out approximate masses, right? Again, this could be really useful in real world situations, because if you have a relationship like this and there are constraints, like I said, either in maybe like distance or weight or what's available to you, you can find something and make it work here. All right. But regardless, remember, we know that this is an inverse relationship. So it's going to have this equation of output equals constant divided by input. Output equals constant divided by input. Since we know this is our relationship here, okay, we know this is our relationship, we could pick any coordinate, plug it in and calculate our constant value. Okay, so when we do that, we find out our constant value is 100,000. Our constant value is 100,000. So what that's saying is when I have my mass and my distance, if I divide my 100,000 by my distance, it should equal my mass. Or if we rearrange our equation, okay, and put distance on the same side as mass, what this is saying is mass times by distance has to give me this value of 100,000, right? 100,000. And what we'll notice here is, again, this is mass times by distance. It has to equal 100,000. And so when we're looking at something like a lever, right, or that basically a balance, both sides have to be equally to each other in order to have that balance. So mass times by distance has to equal mass times by distance, right? It has to equal the same number. Whether we have different distances or not, it has to give us the same product when we multiply them out, okay? So again, the left-hand side here is 900 plus 100 from the pan, so we've got 1,000 grams multiplied by the fact that it's 100 centimeters out. So that gives us our 100,000. So when we're looking at the other side, whatever our combination is, it still has to give us that 100,000. Still has to give us that 100,000. So what we can see here is, oh, I might only have, I might have 2,000 grams, Okay, and if I have 2,000 grams, I only need to be 50 centimeters away in order to be balanced. I only need to be 50 centimeters away in order to be balanced. All right. So then confirming what we just went over here, a function is inversely proportional if you double the input and the resulting output is halved, right? Halved. So then if we look here, a rational function is a function whose equation contains this is the definition that I don't like, a rational expression. Okay? When a function gets closer to a line but never reaching it, that's called an asymptote. An asymptote. That's a new word for us. Okay, and then here, an inverse function is if the function's input is multiplied by 6, then the output has to be, remember, it's inverse. So if we multiply, we have to divide, and it has to be by the same factor. So it would be divided by a factor of 6. Or it would be divided by a factor of 6. So down here, again, you can figure out which of these functions are rational. Again, it has to have rational values, not irrational values. Okay, a couple word problems here. So remembering, what would this look like as a function? Okay, we're looking for width as a function of height. So how would you write that? What would that look like? Okay. Then this here again is talking about asymptotes. What happens to x as x gets closer to 0? So as x gets closer to 0, this graph f of x gets very, very, very large, okay? And it approaches an asymptote, but it's not a horizontal asymptote. It is a vertical asymptote, all right? And then finally here, what are the restrictions on the range of f of x? So understanding that range is talking about y values, and we're talking about f of x. So what's my range, or what are my acceptable y values for f of x? So y can be from here to here, or whatever, right? And again, knowing that when we have these asymptotes, it does not include the point. Okay, so it's never going to equal 0. It has to be greater than 0. Right? It has to be greater than 0. Okay, so taking a look here at our study guide. Taking a look at our study guide here. All right, so again, basic definitions here. Understanding that we can take things from words. We can give ourselves an equation. And from an equation, we can make a function. Right? We can make a function to fit multiple things, right? We can make a function from our words, or a word problem. All right. So, sorry. Again, understanding if we're talking about word problems here, putting some real world constructs to it. So it's got to have an area of 100 square feet, so it can't be negative, right? It can't be negative, and we talked a lot about that with the unit. Okay, so that's why the values can't be negative. All right, and then this again is talking about asymptotes. So things can get very, very small or very, very large as they're approaching an asymptote. Again, an asymptote where it gets really close to, but it never actually touches. Okay, it gets close to, but it never actually touches. So if we look at our checkup here for 1.7, right? If we look at our checkup, okay, just a couple helpful hints here. All right, so answering the question, remembering what's horizontal, what's vertical. Again, what does it get really, really close to? All right, and again, that's going to be in the form of y equals something or x equals something. And if you don't remember what those would look like on a graph, okay, plug it into your graphing calculator or try to put it on this line here. So if y equals 1, what would that look like, right? And then here, being able to answer just general questions, general understanding questions about inverse variations. What actually happens if I divide or multiply something? Remember, it's the opposite function, or I'm sorry, it's the opposite operation, right? If I divide, I multiply, divide, okay? It's the opposite operation, but it is the same magnitude, right? Divide by 10, I'm going to multiply by 10, all right? And then finally here, don't let this one confuse you when it says function notation. Again, just writing it in the form of, if I've got width equals 50 divided by length, okay? I would normally have written length as an L, right? And I don't know why they decided to not do that. But whatever your variable is, it doesn't matter as long as you have it consistent throughout. So right here we're saying that width is a function of x, where x is down here. Or if we look over here, length equals 100 divided by width. So we have length as a function, that's what it means when it's in parentheses, length as a function of width is equal to 100 divided by that width. All right. Hopefully not too terribly difficult. And again, there's one quiz we have to complete right there. All right, so the 1.7. Looking at 1.8, okay, now we're going to deal with those things called vertical asymptotes. Okay, so looking at vertical asymptotes. All right, so we realized that this function had a horizontal asymptote at y equals, we had a horizontal asymptote at y equals 0. And we had a vertical asymptote at x equals 0. All right, so we have two different asymptotes here. All right, and we can look here at our parent function of 1 over x. Ooh, sorry, I didn't mean to zoom out there. All right, we can look at our parent function of 1 over x. Okay, what we can notice here is if I drag this blue dot, okay, it's going to get really, really close to 0 but never touch it. When I get closer to 0 on my x-axis, my y value gets really, really large. And then if I keep moving my cursor over, you're going to notice that at some point when I cross my x-axis, the blue dot comes over to the left-hand side of my graph, right? And it follows that same pattern. So again, I'm jumping across, it looks like I'm jumping across my graph here, right? And the reason that is because there's a vertical asymptote here where x can never equal 0. All right, x can never equal 0, so that vertical asymptote. All right, and if I actually zoom out here, what you're going to notice is that it actually looks like it's at the axes. It looks like it's at the axes. Okay, but if I go over, let's go here, and I zoom in really, really, really close, you're going to notice, eventually if I get on a small enough scale, you're going to notice that it's not actually crossing. It's just getting really, really, really close to. Okay, it's getting really, really close to, but it's not actually crossing. Same thing down here. Okay, it's getting really close to, but it's not actually crossing. All right, so again, this is why maybe changing your windows on your calculator, zooming in, zooming out, okay, could be really, really helpful to you. All right, now we can do this obviously using our graphing calculators. That's kind of always our go-to right now. But if you don't have a graphing calculator, what we can do is we can look at a table of values. So just picking some random values here. And again, what we're going to notice here is that at my asymptote, it's undefined, right? So it's undefined, okay? And then if I look at my graphing tool to the left of that, and the negative x values, it starts really, really negative and gets more positive. On the right-hand side, it starts off really positive and becomes a little bit less in magnitude. Okay, we can notice a couple things there. All right. Now, again, the function where f of x is equal to 1 over x, okay, it's undefined at this x equals 0 point, because again, that's what makes it an undefined function, right, or where we can't divide by that function. All right, so it makes that vertical asymptote. And normally we show a vertical asymptote as a dotted line, okay, but for the sake of clarity here, they're going to show it as a blue line so you can see it very easily, right? So again, the vertical asymptote, as we get close to it, we're either going to get really, really large, like we do on the right-hand side here, or really, really small, as you do on the left-hand side, right? So that's what we're doing as we reach that vertical asymptote, or approach the vertical asymptote. Okay, so then we can look here at other rational functions. All right, and obviously here we're looking for where does the denominator equal 0, right? What value of x would make the denominator equal to 0? So if we look here, first off, obviously 2x on bottom. If x is equal to 0, that's going to make that function undefined. All right, but if I look at over here, x minus 5, right, x minus 5. Okay, clearly in order to make that denominator equal to 0, x would have to be equal to 5, right? So now you can kind of understand as to why when we're talking about functions, we were saying or trying to figure out what values x could not be equal to, because those values that x can't be equal to are now going to give us these things called our vertical asymptotes. They're going to give us our vertical asymptotes. All right, so then How do we graph these, or what would this look like, right? So it's pretty simple here, or at least hopefully I think it's simple. There's 2 steps, okay? Figure out where the vertical asymptotes are, okay? Draw them, right? And then make a table of values to find points on either side of that vertical asymptote. So for example here, okay, I have my graph, my vertical asymptote is clearly going to be at x equals 3. Right? Then I would pick some values to the left and to the right and figure out what those values would equal, and I'll be able to draw a general shape of my graph. Right? I'd be able to draw a general shape of my graph. All right. Again, that's how you would do that one. Okay. So then again, looking at graphing both sides of a vertical asymptote, okay? If I have a function that's 1 over x squared, okay? Clearly, the vertical asymptote is going to be at x equals 0. All right, but what the shape of that graph might look like will be a little bit different because, again, now we're dealing with an x squared. So what that would look like here is it would look like it's reflected across the y-axes. It's reflected across the y-axes here. Again, both of them get really close to 0, but they never touch. They get infinitely larger, all right? So again, that would be how we would draw that one. And if you had to sketch this quickly without a graphing calculator, again, you'd pick values to the left, to the right of that vertical asymptote, plug in and see what you solve and get. Right. Okay. So then here, if we look at playing around with some of these, we can actually pull the position. And so if this is what our equation originally looks like, 1 over x, if I shift my asymptote 2 units to the right, it's going to be just like what we saw with transformations of the graphs, right? I'm going to subtract 2 because all I'm doing is I'm shifting the graph left or right. That's all I'm doing, shifting left or right. So again, remembering that if I'm subtracting, I'm moving to the right, and if I'm adding, I'm moving to the left. All right, so again, it's just basic graphing transformations. All right, so to confirm here, for finding the vertical asymptotes, a function has a vertical asymptote at every value where x is undefined. All right, undefined. That means that the bottom is equal to 0. We can't divide by 0, so that's going to give us this undefined value. And what that means then is that our function is going to get really, really large or really, really small, or what we can say is it approaches positive or negative infinity. So then again, vertical asymptotes, those are those lines where it's going to get really close but never touch. And then we had those quick and easy steps for rational expressions. Okay. So then when we're dealing with finding these vertical asymptotes, right? So given the graph of f of x to the left, what happens to f of x when x goes from -1 to -2? So again, being really careful with how you read this. It's saying when x goes from -1 to -2, what happens? -1 to -2. All right, does it become a very large number? Does it become a very small number? Is it positive? Is it negative? What happens? Okay, what happens as you go from -1 to -2? All right, so then again, here are check our understanding. Basically, can you identify the vertical asymptotes? Where does the denominator equal 0? Or what value of x would make the denominator equal to 0? All right, and then again, identifying them graphically and knowing that, okay, if this is at x equals -1, that means I'm going to have a value that's going to make my denominator equal to 0. And that value is going to be when x is equal to -1. So what would that look like in terms of my equation here? All right, same thing here, but now noticing that it's a slightly different shape, so you still might have to double check on a couple things here. All right, and noticing that it's shifted to the left, so that might be a little bit of a helpful hint there. Okay, so if we move on with this, if we're looking at more than one vertical asymptote, right? So there could be multiple asymptotes in your graph, right? And when we started this, we looked at one that had a vertical and horizontal asymptote. All right, so we can look at what happens if there's more than one vertical asymptote, right? And just to give you the answer, it's any point that would make our function undefined, right? It's any point that would make our function undefined. So if we look here, okay, at our first value, obviously if we have a 0 here, we've got x squared. So 0 times by anything is going to give us 0. So our first vertical asymptote in this function here would be at x equals 0 because that makes the function undefined. All right. But then another point that makes this function undefined is where x is equal to 3, because 3 minus 3 gives us 0, right? 3 minus 3 gives us 0. So that also makes that undefined. All right. So we could have two vertical asymptotes because those points both make this function undefined, right? Or our denominator 0. Okay. So if we're looking at it, then we can pick values on the left and the right hand side of both of those asymptotes and see kind of the general shape of what that graph should look like. All right. So then based on those values here, if we sketched, right? If we sketched this function, okay, you should again hopefully notice that on the very, very far right-hand side. So if we start way over on the right-hand side, because we have our vertical asymptote at 3, right? We would draw our vertical line at 0, draw our vertical line at 3. On the right-hand side of 3, we're dealing with these values. So it looks like I start out really small and then get larger. And then I start out negative and then get larger, right? Noticing all of these things here. All right? So how does this work? Why does this work? All right, and if we look at our graph of g of x, it would look something like this. It would look something like this. Okay? And to me, it kind of looks like a combination of our 1 over x parent function and our x squared parent function. It looks like to me a combination of our 1 over x parent function and our x squared parent function. All right. But again, this shape of this graph is not going to be as obvious, right? Or maybe it is to you, but to me it's not, right? And so that's why we plug in those values, we generate a table, and we can roughly sketch points and see what the shape of the graph might start to look like, right? We can look at what the shape of the graph might start to look like. All right. And again, yes, you can always plug this in your graphing calculator to get a better idea of what this will look like. Okay. So then again, looking at some more examples here, again, to find the vertical asymptotes, it's just anywhere where x would make the input of x value, right, would make our function undefined. So if we look at the first one here, if x is equal to 0 or negative 8, it's going to make that bottom a 0 and this function undefined. So we're going to have our vertical asymptote at those 2 points. Okay. If I have something like g of x here, all right, I could have 3 vertical asymptotes. I've got one at 0, one at negative 1, and one at negative 9. Again, it's just anywhere where that function is going to be undefined. Right? So finding the vertical asymptotes hopefully doesn't seem like something totally brand new here. Again, it's just applying our logic to a new concept. All right. So then if we look here at some rational functions with more than one vertical asymptote, okay? More than one vertical asymptote. Our first one here, I think I can move these. There you go. All right. So I've got 1 over x times x minus 1, right? So I've got a vertical asymptote at 0 because if x is 0, that would be 0, and I have 1 at positive 1, right? And again, same thing. I can move this, and if I move my vertical asymptote, it just changes the value there, right? Changes that x value. But I can also move this guy, and it would also change that function. Can add, subtract, right? So it might take on a slightly different form, okay? But in general, if you have this type of function, that would be what the graph would look like based on its vertical asymptotes. All right. If I have 3 vertical asymptotes, I might look something like this, right? So that first one, that +1, I could change that maybe to a +3, right? Maybe a +3. I've got my vertical asymptote at 0. Maybe that's at -1, right? Just being able to play around with these. And again, remembering that our rules for transforming functions are still in play here, but now we just have potentially multiple places, right? And we're not necessarily changing the entire graph. We're just transforming the vertical asymptotes themselves, right? So we're changing the vertical asymptotes. And obviously the last one here, again, same concept. Okay, I can add or subtract, and that will change where my lines are at. All right. So to wrap it up, a vertical asymptote might exist where a rational function is undefined. Undefined. All right. And then again, to sketch the rational function, okay, you find where the asymptote is, you pick values to left, to the right of it, okay, and then obviously you always want to check the actual value you pick itself, okay, but you pick values to the left and to the right, and then you are able to plug them in, get some general values, and sketch a graph roughly. Okay, so then hopefully you guys can match these up here quickly, but again, it's figuring out how many places or how many values can you calculate for x that would give you an asymptote, right? So for example here, if I've got an x and an x, I can have x equal to 0 or x equals to 2, so that's going to give me 2 possible asymptotes, right? That's going to give me 2 possible asymptotes, right? And hopefully you can figure out the rest from there. All right, so then looking at here, again, identifying how many asymptotes does the graph have, how many asymptotes does the graph have, and checking those values, right? And then looking at graphs and being able to kind of determine what the shape of that might be, right? And again, a helpful hint for this one would be figure out how many asymptotes do you have, right? That's the step. That's the first step. Figure out how many asymptotes do you have, and then figure out where those asymptotes located, right? Once you figure that out, you should be able to match them up to the graph there, right? But again, always, when in doubt, you can pick a couple points on a line and see if they match up where you think they should. All right, same thing here. Figure out where the vertical asymptotes are. How many do you have? See if you can find them with the graph. When in doubt, plug in values. All right, quickly here, because I know we're running out of time, looking at our study sheet here. Again, a vertical asymptote is a vertical line that the function approaches but never touches. Okay, a vertical asymptote is any x value where it is undefined. All right, and then the value approaches infinity, right? It either gets really, really large or really, really small when it approaches a vertical asymptote. Okay, so then looking here, right, as x becomes a small positive number, right, so small but still positive number, our function, right, our output value of y becomes really, really large. Okay, oppositely here, as this becomes a small negative x value, right, it becomes very, very negative. All right, so this point x equals 0 is a asymptote. All right, it is an asymptote. So then again, hopefully we can figure this out. If it's not in this super nice form, right, if it's in our original polynomial, in order to figure out asymptotes, the first thing we'd have to do is factor the denominator. Okay, we would have to factor the denominator. I know most of those problems that we got were already in the nice, already factored form for us, but if it's not, you might have to just do that extra step there. Okay, then we would set each factor equal to 0. We would solve for x, and then that would tell us where the vertical asymptotes are. Okay, and again, we can have one vertical asymptote, we can have multiple vertical asymptotes, and as you're going to find out here, how to make the graph, right? We find the asymptotes, we write them on the line, And then we would make a table of the left and the right-hand side, and then we would fill in the general trend of the function. Okay, we'd fill in the general trend of the function. Okay. So then if we look quickly at our checkup, just a couple helpful hints here. Oh, sorry. So figuring out if it has a vertical asymptote, right? And where those would be located. So that's just setting the factors of the denominator equal to 0. And again, all of these are already factored for you, but if they weren't, you might have to do an extra step of actually factoring. All right. Then here you're going to figure out how many asymptotes do you have, where are they located, and then try to match them up. And again, worst case scenario, you always pick a couple points and plug them into your possible equations and see if they match up with the graph there. All right, hopefully not too terribly difficult. Okay, again, you have two quizzes here. You have a finding the vertical asymptotes quiz, and then if you have more than one vertical asymptote. So those are the two quizzes you have here. All right. If you would like, this journal is extra credit. Okay, so again, this journal is extra credit. You can do it if you'd like. It is not mandatory. Okay, it is not mandatory. Moving on to our last new lesson here, 1.9. Okay, so this is on the graphing of the rational functions. Okay, so a little bit more about graphing those rational functions. Okay. So now we understand that what they have to look like. We understand these new things called asymptotes, right? So now we have to look at if we have a numerator and a denominator, right? How would we actually graph those? Okay, so again, reminder, what values of x would make this function equal to 0? That's kind of the general question here. Okay, what would make this equal to 0? Okay, so we're now asking not what would make it undefined, it's asking what would make it 0. Okay, so again, we worked a lot with, okay, if it's undefined, that means that our denominator equals 0. Okay, our denominator equals 0. If we're asking for our function to equal 0, or actual function to equal 0, that means the numerator or the top has to equal 0. So that would be looking at what functions here, or sorry, what values of x would make the numerator 0. And that should be 0 and positive 3. Right? Because if I plug in 0 here, 0 on top, as long as it doesn't make a 0 on bottom, right, we're fine. So we've got 0 on top. Great. That makes that function equal to 0. I've got a 3 on top. That would make my function 0 as well. All right. So again, going from what makes it undefined to what makes our function equal to 0. All right. Now, looking here, if we look at here, okay, we can see that both of these have similar equations. Okay, so 1 over x plus 1 and x over x plus 1. All right, they both have a vertical asymptote at x equals negative 1. Right, they both have a vertical asymptote at x equals negative 1. But now the difference is that g here will have a 0 point. Right, it will have a 0 point because we can make the top here equal to 0. We can make the top here equal to 0 by having x equal to 0. So if we look at our graph here, so for f of x with no zeros, it looks like this. Okay, it gets really, really close to the line, but it never touches. Okay, for g of x, we have 1 0. We had 1 0, right? At x equals 0, we have a 0 point. So what we can notice is that we have one place where it crosses the x-axis, right? It shifted our graph, and we have one place where it crosses the x-axis, okay? Among other things. Obviously, there is a reflection, right? It's a different shape of a graph, but in general here, we've got our two lines, and again, here, they're not crossing this line. There's no 0 points. This one here, it's still not crossing that vertical asymptote, but now we have 1 0 point at x equals 0, because at x equals 0, our numerator is also equal to 0. All right. So knowing these really important parts of our graph are going to be helpful here. Okay, knowing our points are going to be super helpful. All right, and what they're saying here is that if you were to sketch a graph, so again, let's say I took your calculators away and told you that you couldn't use them for a test. I know it's not possible, but if we were in school, I might have a test that says, okay, no graphing calculators today, or no calculators today, right? So you might have to sketch this. So what they're saying is that you can make this thing called a sign chart, all right? And to give you the definition of a sign chart, right, they're saying it's a chart that records information about the rational function and the values, okay? So it's going to tell you where the zeros are, if the value's going to be positive or negative, and what it might be. Okay? So by that, it means you could draw the key points there, right? So if you had zeros, if you had vertical asymptotes, right, you can draw those points, right? So for this graph here, we had a vertical asymptote at x equals -1. And we had a 0 point at x equals 0, right? Then what we could do is generally look at what would happen if I had values to the left and to the right of all of these major points here, okay? And you can sketch out like, okay, hey, over here, the left of these are all going to be positive output values, all right? Positive output values versus between -1 and 0, these are going to be negative. And then over here between 0 and positive infinity, it's going to be positive, right? And again, how can you do this? You can just either mentally plug some values in or try to, or try to just look and notice. So for example here, somewhere over here, I had x is equal to -4. X is equal to -4. Well, I'm going to have a -4 on top, and I'm going to have a -4 plus 1, right? So I'm still going to have a negative value. I don't actually care what the actual answer is. I know that I've got a negative on top and a negative on bottom. So regardless, I know that my output value is going to be positive because negative divided by negative is a positive. All right, same thing over here. If I've got a positive value divided by a positive value, I know I'm still going to have a positive value. Whether it's going in the positive or negative direction, like if it's increasing or decreasing, I can't tell you, but I know that my absolute output is going to be positive, right? And then lastly here, between -1 and 0, right? These values are going to be negative, and you might be questioning as to why, right? And the reason that is because I have this +1 here. So if I have, let's say 0.5, right? 0.5 on top, or sorry, -0.5. Let's go with -0.5. Okay, so I have a negative value on top, -0.5. Well, if I have -0.5 plus 1, that's going to give me a positive value. So I'm going to end up with negative divided by positive, which is going to give me my negative values. So this is how I can sketch this thing called a sign chart. All right. Again, I know it's not super applicable right now because you guys have your graphing calculators at all points, but you still got to know how to be able to do this. All right. So again, step 1, find the zeros and the vertical asymptotes. Okay, great. We found those. Then you're going to pick numbers, right? Pick and test numbers. So I picked -2, -0.5, and 1, or they picked it. Right? And you're going to figure out, okay, is it going to be positive, negative, or positive, right? So exactly what we were talking about. Then what you can do is keep in mind that it's going to remain positive or remain negative as long as it doesn't cross one of these major points here. All right, as long as it doesn't cross one of these major points. So again, example, this over here, the -2 was going to be positive, right? It's going to be positive. So if I kept going, -5, -30, right? As long as it doesn't cross another major point, it's still going to be this positive value. Same thing here on the other side, it's still going to be positive. Okay, so then what we can do here is we can then use this sign chart to create our graph. Okay, so we now know, again, where the zero and vertical asymptotes are, where the function's positive and negative, and we know the value of the function at each of our test numbers, right? So we knew what -2, -0.5, and 1 would look like. So again, we could fill in those general points and we can see, okay, hey, this is what the general shape of my trend is. I know my vertical asymptote, this graph is going to get really close to but never touch, really close to but never touch. And then again, we can draw the general shape, okay, the general shape. And if we were in a class that I was teaching, 9 out of 10 times, this would be more than enough of a graph if I asked you to draw me a graph here. Okay, so you don't have to always spend so long picking out, 10 or 15 different points that are exact. Just pick a couple. As long as you have the major points and the major characteristics of the graph, it's going to be more than fine. Okay, so that's a quick way of sketching those graphs here. All right, so again, if we were to look sign chart, you pick out the major points or the major features on the graph, right? You pick out a couple points in between, you solve for them, and then you figure out what the positive and negative outputs are going to be, and then you can generally sketch your graph. All right, so I will let you guys look at that more in depth here, just for the sake of time. I don't want to spend too long, but again, there's a couple good examples here again. So just finding the zeros and finding the vertical asymptotes. So remembering that, again, zeros are where the top is equal to 0, and then asymptotes where the bottom is equal to 0, right? So finding those major points, okay? And then being able to, once we found those major points, pick values in the middle, okay? Pick values in the middle, figure out what the answers are going to be and if it's positive or negative. And then you can fill out the rest of the table. So this value was negative, so it's going to remain negative until it reaches this vertical asymptote. All right, on the other side of the vertical asymptote, we found out that this value is positive. Okay, so all of these values in between two major points in the graph are going to be positive, right? And it doesn't mean that it can't stay something. So one thing I want to point out here is that between 0 and 1, it was negative. Right, so a 0 was one of our major points, and so was this vertical asymptote. Okay, on the other side of the vertical asymptote, though, between 1 and our other 0, okay, between our vertical asymptote and our other 0, it's still negative, right? It's still remaining negative. So it's not always that you're going to flip signs, but at these major points, you have the opportunity for flipping signs. Okay, so again, it's not always going to be negative, positive, but there is the opportunity to flip signs. All right, once you have the general shape, or sorry, the general trend, you can draw your major parts, you can draw your points that you found in between, and you can draw a general shape of your graph there. All right, so then again, taking a look more at these asymptotes. Okay, so I can again, ooh, that was neat. All right, I can pull my 0 point. So right now, if I start out, I have x on top and x plus 1 on bottom. So this again, my 0 point is at x equals 0. If I pull my point, right, I now start shifting my top value, right? If I move to the right, I'm subtracting. If I move to the left, I am now adding. Okay, so again, this is just a general shape. The bottom is not changing, right? My vertical asymptote is still there. My vertical asymptote is still there. All I'm changing is where the 0 on my graph is located. All right, looking here, I can pull, same thing. All right, I can still pull, same thing. I've got 1, 0, 2 asymptotes, right? And I can change where that 0 is located. But notice here, I go from x minus 3 on top to x, right? And if I get on x equals 1, right, if I put my 0 right on that vertical asymptote, Okay, hopefully what you're able to notice, that vertical asymptote is still there. Okay, that vertical asymptote is still there. And we talked about this a little bit, all right, but you see how it's an open circle? It's an open circle because it's not included, right? Only when it's a closed circle is it included. The reason, again, it becomes open is because it's on our line, right? So there's no, it wouldn't be included as a value, all right? Same thing, again, we can still play around with all of this. The bottom isn't changing. Okay, the bottom isn't changing. What's changing here is noticing where my value crosses the x-axis. All right, so a sign chart can help us graph a rational expression. Okay, and I'll leave you to explore that more in depth here. All right, so then sketching the rational functions here, okay? I'll let you guys again do this one here to test that you know what's going on. But in general, find the major points, find the asymptote, find the zero, okay? Then you would, we could then, sorry, pick test numbers, right? We can pick test numbers between the major points, right? We can solve for what they are, figure out if they're going to be positive or negative, okay? And then we can sketch our graph as needed. Okay, we can sketch our graph as needed. All right, so same thing here. Again, figuring out, really being careful too if it's asking you for a zero or if it's asking you where something is undefined. Okay, so where would it have a vertical asymptote? That's where the function is undefined. So where is the bottom equal to zero? All right, and then being able to identify those major features in the graph. Okay, so again, we're now adding on a little bit more. Now we're not just looking for where we have our asymptotes, we're also looking for where, if any, do we have any 0 points. Okay. Sorry. All right, so just as we did with having multiple asymptotes, we can also have multiple 0 points. Okay, we can have multiple 0 points. So if I move, right, I can still move. And as you're going to notice, the denominator isn't changing, right? If we move the 0 point, we're just changing the numerator. Right? We're just changing the top value there. Okay. So then this is what we were talking about a couple slides ago here. All right, this thing where it says a hole or an open point, right? An open point. Okay, because what we're going to notice here is that at this value here, at this value of x equals -1, okay, x equals -1, that makes our top, our numerator, that would make our numerator 0. But also, it makes our denominator 0, right? So this is the point where we have a 0 point and it's intersecting with our vertical asymptote, okay? So it makes this thing called a hole in our graph, okay? And it could be called a singular point. Okay, it's called a singular point. And the reason that is because it has the same factor in the numerator and the denominator, okay? And normally, at that point, it would be undefined. It'd be undefined, all right? But it would be undefined, and since it has this point where it's supposed to be crossing the x-axis, we draw it as an open circle, right? So it's no longer closed. Closed means that point's included. Open is not, because again, remember, we have a perceived vertical asymptote at that point. All right, so then looking here at our similar factors. Okay, looking at our similar factors, we obviously have an x plus 1 on top. All right, so we can cross those out, and we can say this is our function when x doesn't equal any of those three values, right? So even though we might simplify our product, we still can't have x equal to -1. We still can't have x equal to -1 because we have to look back at our original expression there. Okay. So same thing here. Our simplified version of f of x looks similar to g of x here. All right, it looks similar to g of x, but let's see what happens when we look at them graphically. So f of x has that hole in it, right? But g of x, okay, g of x doesn't have that hole, right? That point is included. So what the heck is happening? Well, the reason, even though they're simplified and they look the same, the reason is because f of x originally started out with this x plus 1 on top and on bottom, right? And so we can't just ignore that. Even though our simplified version looks like g of x, we still know that there is a hole and a vertical asymptote there, right? We still know that. So the functions look similar, but the difference being that in g of x, since this was the original expression or equation, there was no vertical asymptote, there was no 0 point, there was no hole, right? So that's the only difference between those two graphs here. All right, so if you see a hole on the graph like this, right, that would tell you that should tell you that you have a common factor in the numerator and the denominator of your function. All right, so same thing here, right? Remember, if I pull, okay, if I pull, for that one, I know it's a bad example because there's only one, but when I have my 0 point reaching my vertical asymptote, it makes a hole, right? It makes a hole. So 1 plus x plus 1 over x plus 1. All right, x plus 1 over x plus 1. And normally, this would be 0 over 0, okay? But we know it's undefined. So what we would do is we'd look at points around it. Okay, we look at points around it. So if you notice here, if I get really, really close, here, you notice that they start to look like they're going to touch. Okay, so again, we draw it as a hole. We draw it as a hole where the line is perceived to be. All right. Same thing here. So if I pull this closer, you can see that these graphs look like they're going to be touching at that point. If I were to connect those two graphs, I know it's hard, but if I were to connect those two graphs, look about where they would be. So it shows it as a hole where those two would touch if they came together. Same thing on this side. Looks like they're going to touch a little bit above the x-axis, and that's where that graph would be. Okay. Same thing with the rest of them here. Okay. So again, you can then play around with moving, right? Moving the asymptotes, and we know that that changes the bottom. We can play around with moving the x where it crosses the x-axis or the zeros, right? And we know that that plays around with the top values. Okay. So then to wrap up this section here, okay, quickly with our study guide, we have the difference between looking for zeros and looking for our vertical asymptotes, or where our function is undefined. All right. So again, we're looking either at making the numerator equal to 0, that would be looking for our zeros, or we would be looking at where our denominator is equal to 0, and that would give us our vertical asymptotes. All right, so that's what that's saying right there. Okay, then what we can do is test both sides of each zero. Okay, so this is talking about making that number chart or the sign chart. Okay, so if I have my vertical asymptote here, my vertical asymptote here, and I have a 0 point, right, I could pick other points in between, right? And theoretically, you would have also identified -1 as a 0 point if you knew the equation here. All right. So again, right here, this is our equation. So we know that -1 and +1 would give us a 0. So this would already be filled in. And then for our testing points, right, we would pick points somewhere between our vertical asymptotes and our zeros, right, any major points, and we would test them to see what the signs are. Okay, and then since we know that we have signs, okay, the signs are going to be consistent. Until they reach a major point, either a vertical asymptote or a 0. That's where they can change signs. They don't have to, but that's where they can change signs. All right, and then after that, you would sketch the major components and then those test points that you picked, and you'd be able to generally sketch the shape of your curve. All right. And then the last thing we talked about is a singular point where the numerator and the denominator both equal 0. Okay, so that's where we have this hole. That's where we have this hole. Okay, and we draw the hole as if it's the point where the two graphs were coming together, right? So that sliding tool showed us it looks like they're going to touch at this one point if I kept going closer and closer and closer to that asymptote. Right, so that's where we draw our hole, because obviously if we plugged in -1, okay, if we plugged in -1 for our x value, right, we would end up with 0/0, okay? But since it's at a place where we have a vertical asymptote and a normal 0, we draw it as a hole where the graph would continue if that was possible. So then looking at the checkup here, because I know again I'm running out of time. Looking at the checkup here again, find the zeros and find the vertical asymptotes for the function. Okay, be able to look at the graph and figure out which is its function. Okay, so again, identifying zeros, identifying vertical asymptotes, and then again, if necessary, picking points in between and plugging in to figure out which is the points. Okay, hopefully not too terribly difficult. All right, so last thing, you have this quiz right here for 1.9. All right, so in class today, we covered 1.7, 1.8, 1.9, so you are responsible for those quizzes. All right, additionally, what I would like you to do is take your Unit 1 CST. All right, so today's got a little bit more homework than the last couple of days. You've got the quizzes for 1.7, 8, 9, and then once you've completed those, you have your Unit 10 test. Okay, you have your Unit 10 test. All right, so I will unlock those as I can, and if I haven't unlocked yours when you need it unlocked, please send me an email so I can get on that as quickly as possible. All right, but again, we've covered a lot of information in the last 3 days, so please make sure that you are up to speed here with us. Okay, so try to keep up to speed here with us. All right, and then we'll keep rolling. So tomorrow, for class on Thursday here, we will start with Unit 2. Okay, so again, I'm expecting tonight for you to finish all the way up through the CST for Unit 1. Again, your TST is not mandatory, and any journals or practice assignments are also just going to be extra credit. Okay.